So again, Le Chatelier's principle is the theme. I like to summarize it this way. When a chemical system at equilibrium is disturbed, and then the system will act to counter or reverse the change. That's what we're going to use, whether you have a concentration change, a heating, cooling, temperature change, or pressure volume changes. We're going to come back to this statement. And we're going to start with talking about heating and cooling and predicting what the shift would be. Now, my first example, I just wrote exo as a short for exothermic. Okay. Exo in science always means out, where endo means in, and you see it a lot in biology. So this is an exothermic reaction, which just means energy is coming out. So I put an energy term on the product side. If you had an endothermic reaction, then we're going to see our energy term as a reactant. And we're really just treating that energy as a reactant or a product. So I want to answer the question in red, what happens to the equilibrium if the temperature is increased? So we're going to think of this, what is the stress? Okay. We're heating it, so we're just going to add energy. And that's why we need to know what side the energy is on to be able to predict the shift. Okay. So what happens when the equilibrium, when the temperature's increased? Well, it's going to want to do the opposite. The equilibrium will shift in the direction that cools the system. Okay. That would counter or reverse our change. So we want to get rid of energy. We want to cool it down. Okay, so we added a product, and it's going to want to shift towards reactants to try to use up some of this energy. But as a consequence, it's going to use up some sulfur trioxide. Okay? And it's going to make sulfur dioxide and make more oxygen gas. Okay? Everything has to go with it. Even though the energy is driving it, everything changes. So you need to be aware of, again, all the chemicals. So there's less sulfur trioxide because that's a product also. So we're going to see the energy go down. We're going to see that go down. That's going to go up. That's going to go up. And I'm just summarizing that down below. Okay, more of our two reactants. Now my second example will be endothermic, but none of the science, the theory, the principle changes. Okay, if it's endothermic, we just have an energy term on the other side of the equation, and we use the exact same thought process. We want to do the equal system will do. It's not that we do, the system will do the opposite to our stress. So I'm just using the first suffix from endothermic is the term you might see. Just reminding endo means in, okay? We see energy coming in, and it's a reactant, or the starting materials, or the things that go into the reaction. So what happens to equilibrium when temperatures decrease? I'll try to keep my same color coding. So I use purple to denote the stress. Okay. So our stress is energy going down. We're removing energy. The system will want to do the opposite of removal. It'll want to replace. We've got to replace energy. So that would be shifting towards the energy to replace it. Okay. This is just like a remove a reactant that was in a few stations of the lab. As a result of that cooling and then a result of the reverse switch, the reverse shift, we're going to end up seeing more reactants and less products. And those green arrows are summarized in my bottom two bullets. Now, it came up in the lab, was a good question, like what exactly are reactants and what are products? Because in this reaction, these are reacting to make those. Okay? But the definition that science, chemistry uses is anything at the beginning we're going to call reactants. Anything at the end, on the right, we're going to call products. And we now make statements like the products turned into reactants. That's the vocabulary we'll use for a reverse shift. In the second part, the following lesson, going to look at graphical analysis and figure out what happens. So I just want to do a little preview of coming attractions with what this will look like graphically. So I have time on the x-axis. So just think, you're in the lab, you have, you had the conditions at the beginning, you did something, and then you had a new color at the end. So that type of timeline. But instead of just looking at colors, I'm going to have concentrations. Square brackets is a short form for concentration. So what we would see graphically, and I'm just going to pick one reactant and one product. Let's start with NaCl, and I'm going to pick an arbitrary starting point. I'm going to put HCl. I'll say that concentration is a little lower. And at the very beginning, before the stress, we would have a flat line. Okay? A flat line where the concentration isn't changing is indicative of being at equilibrium. No, this is dynamic equilibrium. The reaction is going forward and backwards, but at the same rate that you see a constant concentration. But it doesn't mean nothing is happening. It's just the forward and reverse balance each other out. Okay? In this course, for testing purposes, it's assumed that the stress always happens instantaneous. That's not true in real life. So the heating and cooling for the half the class that saw that yesterday, it didn't happen instantaneously, but on a test, it's going to, or you're going to graph it as if it happens instantaneous. Okay, when you add it drops, a lot of times it happened in, it happened in a second, and we're going to treat it all happening right at this dash line. Okay. And now, so what happens? The NaCl is going to start being made. Okay, so this stress is an instantaneous cooling. The reaction will start shifting. It will take time to shift. We'll start making more NaCl. So you'll see it curve as it's being made, and then it's going to level out. I went up because we're making more NaCl with the shift. And then it's going to level out at a new equilibrium. So I'm saying at equilibrium there, they're different values. It's a new equilibrium system because we messed it up. The HCl is going to go down because this shifted backwards. So it's going to take time, and then it's going to level out, and it will go to equilibrium where we see a flat line. Okay. The stress happens instantaneously. The shift doesn't. It takes time. The chemicals have to bounce into each other, collide, in order for the reaction to occur. Second, concentration changes. So that same statement, just repeating, okay, if the equilibrium is going to shift to counter the change in concentration. It's going to do the opposite. Okay? So let's do two quick examples again. This is probably the easiest one, and students have very high degrees of success of concentration changes. Okay? Concentration is the second most difficult, and then we're going to do pressure volume changes, and that's where students will make the most errors. So I have H2 gas plus I2 gas is in equilibrium with 2 hydrogen iodide gas. We used that for our case study way back at the beginning of this unit. And what happens to the equilibrium when hydrogen gas is added? They're all gases, so you'd have to physically pump hydrogen gas into this system. So our stress is going to be to add hydrogen gas. We pump more in, its concentration is going to go up. Okay. So the equilibrium is going to shift to try to undo that added hydrogen, which would be to lower the concentration of hydrogen. Okay. So it's going to shift to consume it. If you consume it, you want it to be a reactant. So we want it to go in that direction. That will make the hydrogen gas be what's consumed, which would be the forward direction. which causes the hydrogen to start going down. It causes the iodine to go down as well, and causes the hydrogen iodide to go up. Now, I intentionally made my green arrow on the hydrogen small. Okay. It's not going to use up all the purple. In the end, there'll be more hydrogen, likely, but the shift is still to use it up. Now, one thing you're going to have to be aware of is, when does the Kc value change and when does it not? When you add or remove chemicals, you do not change the equilibrium value. So that would be the equilibrium law expression. Okay. And with concentration changes, Kc is the same. Okay. Hopefully we saw that in our case study. It didn't matter whether we started with all products, all reactants, we always get the same Kc value. When you stress the system, you're adding a denominator, more denominators. You'd make this expression go down, and the values are going to shift to drive that value back up. So maybe you're at equilibrium and the value is 50. You do something to it, you're not at equilibrium, and this value, it's not the equilibrium law expression anymore, it's not the constant because you're not at equilibrium, but maybe the value drops to 30 and it's going to shift and go right back to 50. Okay. All of these pieces will have new numbers, but this ratio will go back to 50. If that's what it was before, it'll go back to 50 at the end. Okay. You might think, well, this is going up and that's going down, so does it get bigger? Well, no. We added a whole bunch of this, these two pieces shift anyway to get back to that same number. Okay. When you change temperature, you change rates of reactions, you change equilibrium values. Okay. And that's why we heat food to cook it. We want to change the rate of reaction, and we change the actual balance of products and reactants. Okay. If the reaction shifts forward in a heating and cooling, you're going to make Kc bigger. If the reaction goes backwards in a heating and cooling, you'll make Kc smaller. When you go forwards, you make more products, more numerator, and that'll drive Kc bigger. If you go backwards, you're getting rid of product, and products are on the numerator. So you make the numerator smaller, and Kc goes down. Okay? So you need to be able to make those predictions, whether Kc will go up or down, if it's heated or cooled. If it's concentration, you just doesn't change. You don't have to think about it too much. You just have to realize this. Last concentration one, I'm just doing the opposite. What happens when iodine is removed? Okay. Now, the iodine doesn't have to be physically taken out of the container. If you run a reaction and the iodine somehow turns into 2-iodide, that counts as a removal. And again, you saw that in the lab yesterday, and it's why I like to do the lab first. Okay? You had a lab where there was chloride, aqueous. Okay? And you didn't take the chloride out of the container, but you killed the chloride aqueous by making silver chloride solid. AgCl salt. It was a white precipitate in one of the stations. So again, it doesn't have to come out of the container. You just have to not have that exact ion and the exact state, and that counts as a removal. It's very rare you actually take the chemical right out of the container. That is often difficult or impossible. So what happens to the equilibrium when you remove iodine? Just flip up to react. So now you're taking away a reactant. So it's going to shift backwards this time to try to replace it. We're going to get the opposite shift to the first example. So it's going to shift to make more iodine. That's the opposite of removing. Remove, make, that's going to be reverse to make more reactant, which will cause more hydrogen gas and less hydrogen iodide. So you're going to have to use your Chem 30 solubility skills a bit in this course. Okay? Most likely, I'm going to test you on removals that you've seen between the lab and your homework. You're going to have seen them. And we try to cover, your Notre Dame teachers, all the chemicals, the removals you typically see on a diploma. But you could write your diploma in April and get something you haven't seen before. Okay? If you see a chemical on a test and that's not one of the chemicals in the reaction, so you should be thinking, what is it removing? And if you're not sure what it's removing, you got to go looking around the solubility table and try to figure it out. Okay? You've got acids will destroy bases, bases destroy acids, and then you've got solubility. Okay? Silver and chloride is one of the most common that you will see, and it's in the lab. Okay? Last one slide before you're going to be practicing. You did not get to see pressure volume changes. It's just they're very difficult to do in the lab with the equipment we have. Pressurized vessels, gases tend to be clear. So you don't have prior background knowledge from the lab going into this one. Okay? But we still have the Chatelier's principle. We expect an offset. Okay? Now we've got to just quickly go through how pressure and volume relate to each other before we go through the effects of pressure volume changes. I'm going to use a bunch of math language. When volume increases, so if you have a container and you make it bigger and you keep everything else the same, the pressure inside is going to go down. You got the same gas molecules, but now it's in a bigger container. So volume goes up, pressure goes down. And the opposite. If you squeeze, I don't have any balloons left, but if you squeeze a balloon, we've all probably done that, and you drive the pressure up inside. Okay. Math-wise, we'd just say pressure is inversely proportional to volume. Is that language you're used to? If something is directly proportional, it means they go up together and down together. Okay? My kids, their age and height are directly proportional to each other. The older they get, the taller they get. Age goes up, height goes up. Okay? This is inversely proportional. One goes up and one goes down. So even if that terminology is new. At the very end, I'm going to add concentration to this and see what the pattern is of concentration. We'll do that at the very end. Okay. So here's a reaction, and we have a stress. So we got sulfur dioxide, two of them reacting with one oxygen molecule, making two sulfur trioxide. They're all in the gaseous form. What happens to the equilibrium when volume goes down? Now to do Le Chatelier's principle, we're going to have to think of it in terms of pressure. You'll often be told what the container did, but pressure is how we have to do the science. So what happens to the equilibrium if the pressure is decreased? Well, the stress is really driving up the pressure. This is what happened. Volume decreased, pressure. You got to think of those together. And they're inversely proportional to each other. Volume went down, pressure went up. So if we drive the pressure up with the stress, Le Chatelier's principle says it's going to shift to try to drive the pressure back down and try to undo. Okay? The stress can't change the volume. Okay? If I have a rigid box that's a certain size and I can shrink the box, the chemical system can't go and move the box and change the container. Okay? So we can't think in terms of volume. Okay? But it can make more or less gas molecules, which will change the pressure. So this black line is just repeating what I wrote there. Pressure increases, that's part of the stress, so the equilibrium is going to try to do the opposite. It's going to try to drive the pressure down. This is just a statement of the stress, but in terms of pressure as opposed to volume. Okay. Then there's a comma, and then there's the result, then there's the shift. And then we got to figure out how can we lower pressure. To lower pressure, reaction will shift to make less molecules of gas. If you have less molecules, pressure goes down. Chem 20 kinetic molecular theory, we don't care how big a molecule is. We treat all ideal gases as points, whether it's tiny little hydrogen gas or propane gas, which is way bigger, 3 carbons and 6 hydrogen. We treat them all as a point source. Their size does not matter. Their mass does not matter. It's just how many you have. So which side has less gas? Molecule, there's 2 of them, or it'll have a 2 ratio. It's best to just think of this as moles. 2 moles of those, 1 mole of those makes 2 moles of those. So if we go to add up our gas, we've got 2 of these and make sure it's gas. If this said solid or aqueous, we wouldn't count it. But there's 2 gas molecules plus a 3rd one. So there's 3 gas molecules in total on the reactant side. So you should be expecting a question like this, but to have one of these not be gas, and don't count it. That's just down at the bottom. If I had liquid water, that doesn't affect the pressure. Okay? Or a solid precipitate, or just a solid, that doesn't affect the pressure. So you've got 3 gas molecules. This side, that's a gas, and there's 2 of them. So to lower the pressure, the shift forward was correct. We want to take 3 gas molecules and turn them into just 2. And then there'll be less pressure. We're getting that forward shift, more products, less reactants. Now I'm just doing one example for this, and this is the practice that you'll probably ask me the most questions. So you've got to think of pressure, volume changes. You'll often be given a volume change, but immediately realize what is the pressure change. So that's part of the stress. The pressure will do the opposite. If there's a tie for gas molecules, there's no shift. It will stay exactly the same. So if there's 3 gas on each side, no shift. So that's one case you've no shift, is if you change the volume and the gas count's the same. Okay. Another time you'll get no shift is if you add a catalyst. We're going to do rates of reaction 2 units from now. And that's what a catalyst affects. Okay. How fast a reaction occurs. Okay. But it does not change equilibrium values. Doesn't make more chemical, it just gets you there faster. So if you see the addition of a catalyst and you're asked what happens, the answer is nothing at equilibrium. If you're at equilibrium, you can't get anywhere faster. You're already there. If you're not at equilibrium, well, you'll get there a little quicker, but it doesn't change equilibrium values. Okay? We're not studying speed at all, so catalysts don't affect anything we're studying at this point. So catalysts are one thing that has no effect. Another thing that has no effect is if you add an inert gas. I'm just kind of squeezing this in. And I sometimes don't emphasize this enough. It's kind of boring. It doesn't come up much, but it's often on your diploma, so I need to make sure. If you pump in any gas that doesn't affect the reaction, you're not going to see a change in shift. You'll drive the total pressure up, but what we really care about is called partial pressure. What is the pressure of each gas? Okay? So there's a certain pressure of oxygen in this room. If I pumped in some more argon, the total pressure in this room would go up, but if you look at the pressure of just the oxygen in this room, it wouldn't stay the same when you add another gas. So if there's, 20 psi, pounds per square inch of oxygen, and I pump in 5 psi of argon, okay? The total might go up to 25, but you still have 20 of the oxygen. The pressure of the gases that are actually reacting don't change.